final speaker of this session is Richard Krumpolec. Do I pronounce it correctly? I won't be able to pronounce it correctly. So, Richard is a researcher at the R&D Center C plant at Masaryk University in Brno in the Czech Republic. He's focusing on the research, development and applications of dielectric barrier dischargers for plasma surface modification, plasma assistant deposition of thin films and plasma functionalization of materials. Mouthful there. Recently he presented a new low temperature DCSBD linear jet plasma technology designed for plasma surface modification of complex 3D glass surfaces and glass fibers and fabrics, but I think he will talk all about it and explain us what it all means. Richard, the floor is yours. Thank you.
Good morning. Thank you very much. The pronunciation is Richard Krumpolec. Just to know. So, thank you. In this talk, I would like to present you our atmospheric pressure plasma technology for surface modification of glass. I will focus mainly on flat glass planes, but also I will talk something about the glass fibers and fabrics. This is the outline of the talk. I will introduce first the DCSBD atmospheric plasma technology. I will show you how we can utilize it for surface modification of glass, and then I will give you a couple of examples, mainly focused on laminated glass. I came from a C plant. We are R&D center at Czech Republic. We are focused on research and development of atmospheric pressure plasma systems. We are doing the basic research in this field, but then we also try to utilize these plasma systems for surface modifications of materials. And one of the applications is glass, and I have a personal attitude to this material because of, for example, this is the first material I was starting working with since my early stages at the university. I'm not an engineer, but I'm a plasma physicist. This is my background, so let's start. Regarding the glass, a very important characteristic of this material is surface. When we want to utilize it, for example, for some coatings, when we want to create some good bonding, for example, for the laminated glass structures, and therefore the properties like cleanness, uniformity, and some good functionalization is very important. The typical way how we can do it is are some wet methods like water cleaning, some solvent cleaning, and so on. But there is also alternative method, or might be alternative method, like utilization of plasma. There are various types of plasma. You can generate plasma at low pressure in vacuum system. This is very complicated and expensive, but plasma can be generated also by a very simple way. At atmospheric pressure without any vacuum systems on large area, and this is the type of plasma which we are developing. And here in this slide I would like to very few words introduce this type of plasma. But first, what plasma is. Basically plasma is the ionized form of gas where various energetic species are present, like electrons, ions, some metastables, radicals, for example. But in our particular way, we are generating plasma at atmospheric pressure where we have low energetic heavy particles, like ions and atoms, but very high energetic electrons, very light particles, and together with the radicals, UV radiation, some metastables, we can introduce this to the surface and initiate some plasma chemical changes on the surface of the material. Our plasma system looks like this. I don't want to, it would be very time consuming to explain you the how this works. Basically, you can imagine this is like a system using which you can generate a thin layer of plasma on the area of roughly 8 to 20 centimeters. And you can generate this plasma in ambient conditions without any special gas. Of course, if you require some special application, you can work with oxygen, you can work with some special gases, but you can generate plasma also in the laboratory air. You can do it at atmospheric pressure. And given by the geometry and the characteristics of the way how we generate plasma, we can achieve very high power densities in our plasma system, which allow us to use very short, you will see very short plasma treatment times. With this configuration, the plasma is generated as a thin layer of the plasma, of the electrical discharge. Originally, this system was developed for a completely different application, for fabrics and this type of materials, but it turns out that there is a very nice effect also on the glass. For large area treatment, it's not necessary to use only one plasma unit, but you can scale it up. You can create a plasma array like this, for example, and you can utilize it for really large area treatment of large glass panes, for example, in automatic inline process. So let's go next. And what is the typical effect of plasma on the material? The basic effect is, as we can see here on this surface, you can turn the material from hydrophobic to hydrophilic. You can clean it, and this is the typical result when we expose the glass surface to the plasma. Since in this configuration this plasma is generated as a thin layer, as we can see here, we developed a special unit, a special tool, using which our plasma unit is kept a constant distance, very precise distance over the flat glass without any direct contact with the glass surface to remove any contamination, for example. We are using a system of air bearings like we have it here. And using this system, we can move over the surface without any friction, without any damaging of the glass. The effect of plasma on the glass is, okay, we can turn it, we can clean it, and we can create a nicely uniform, very hydrophilic layer on the glass surface. We clean it, we remove the, for example, carbon concentration, we initiate some oxygen-related bonds on the surface, which in turn improve that hydrophilicity. In result, we also improve the adhesion force on the glass surface, and we do it on the both sides, on the air side and also the thin side. What is very important is also the uniformity improvement of the glass surface, because of when we do the cleaning, we want to maintain that the surface will be uniform, homogeneous. And using these images, I just to try to show you that we can do the cleaning, and we also improve the uniformity. Here we have the XPS data, which tell us about the concentration of surface carbon, oxygen, and silicon on the glass surface. This color change represents the decrease, for example, of the carbon and to the less concentration of carbon, and increase the oxygen to carbon ratio. This is the carbon signal. And when we compare this image to this one, we also clearly see the improvement of the uniformity, for example, when you compare here. Unfortunately, this display doesn't look so nice, for example, it's over there. When we create surface like this, then we can use it for some subsequent application, for example, and one of them might be the subsequent deposition of coatings. And if you are interested in this topic, you are very welcome to the talk of my colleague, Slavomir Sihelník. He will talk at stage 2 and coatings about plasma treatment of glass for some subsequent deposition of coatings on very thin flexible glass surface. So let's treat our glass panes by our plasma and we can utilize it for laminated glass samples. So I have here a couple of results. We created laminated glass by standard soda lami glass. We can work with air side or thin side. We treated the samples with very short treatment time, only just 4 seconds. The laminated glass here, we work with PVB interlayer, and we measured the maximal force applied on the samples, and we can see that after the plasma treatment, there is a significant improvement in the maximum force measured by 40%. And this is given by the improved interface adhesion between the glass surface and the interlayer. It's possible to work also with various types of interlayers. Here I have another test. This is a pendulum test done on the large sheets created by the centric glass ionomer interlayer. In this case, we work with the air side, also very short treatment time applied. In the case of reference samples, we had to use the primer, of course, but when plasma was applied, we used no primer. And here we have the result after the pendulum test. The samples without any plasma treatment, with just primer application, failed the test, as we can see here in these pictures. And here there is, of course, there are some cracks, but there is no like direct breakage of the sample. It's also possible to treat not only the glass, but also the interlayers, for example. In that case, we can also do some cleaning. We can change the surface-free energy. We increase the polar component mainly. We improve the adhesion force. What is very important that we didn't change the optical parameters of the interlayers. And from the practical point of view or application, it's very nice that we can create, for example, our plasma system in this curved geometry, and this is compatible, for example, with roll-to-roll systems when you can treat these interlayers in line or in roll-to-roll fashion. And here I have result of the drop ball test on the samples where both glass and interlayer was treated by our plasma system. This is the reference sample without any application of plasma, just standard cleaning, and this is the result when the same test was applied on the sample with plasma application. So very big difference. Again, this is done by the interface improvement between the interlayer and the glass. So far, I was talking about this plasma system, which is suitable for flat glass, but it was, let's say, some drawback of a technology that for a long time we didn't have a technology for treatment of very complex 3D glasses like the bended glass or glass used in automotive industry. And therefore, recently we developed a modified plasma system. It's based on the same technology, but at this time we are generating a plasma jet. We call it a DCSBD linear jet, but on the other hand, in comparison to another plasma jet system where a point-like jet system is generated, in our case, we are generating a stream linear jet system. You can imagine it like a plasma curtain, something like that, and which is suitable for line treatment of very complex material. Like here, we have a glass surface, for example. And at the next slide, I just want to show you how plasma very efficiently changed the interface between the glass and on some matrix or polymer when we create the composite material. And since this tool, we use the micro-CT method for analysis. It's not very good for flat glass. I decided to study the glass fabrics and glass fibers. We created the composite, glass fiber composite, using S-glass fibers and with some resin. Unfortunately, I can't talk. Maybe in person we can talk more. We used a vacuum-assisted method for fabrication of the composite materials, and we analyzed by micro-CT the uniformity of the bulk composite material, and visualized the number and size of the voids in the composite material. In case of reference sample, we observed a lot of defects in the material. But when we treated the samples by plasma, you can see that there is a smaller number of defects of these voids visualized by these balls. And also, there is a significant difference between the plasma application. When we treated with this surface plasma, when each ply of the glass fabrics was treated, we significantly improved, we decreased the number of voids. But using this plasma system, this linear jet plasma system, we were able to treat it at once. All the stack of multiple layers of glass fabrics, they were treated at once. And as you can see here, there is a nice uniform composite material without any voids in the material. So I hope I just show you our atmospheric plasma technology for surface modification and activation of glass materials. Plasma has very nice capability to improve the glass interlayer between for the laminated glass or for some composite materials, and we hope that maybe in future we will show you some real application where plasma will be installed in some real production line, for example. And I will conclude that I hope that I have shown you that such an invisible thing, very often invisible thing like a plasma, can change very visible change in the material. Thank you very much. This work wasn't done only by me. It was done also by my colleagues from also another institute. Thank you very much for example, Institute of Aircraft Design. We have very nice collaboration on the composite materials. And if you have more questions, you can contact me and we can discuss more details. If you're interested, for example, in details in adhesion improvement, for example, for automotive glass, we can talk. We have very nice results. Thank you.